This video is going to cover sampling fractions, which are a useful thing to think about when you're trying to do really anything with sampling, where you're trying to have either your entire group or some subset of your group representative of a population. So, like with a cross-sectional study, in order to avoid selection bias, you need like the distribution of exposure and outcome in your sample to reflect that in the population. There's other scenarios where you're more interested in a subgroup of your sample. So basically, you sample like all cases in a case control, but you want your controls to be representative of the population they came from. So basically, sampling fractions is a way to conceptualize how well your sample is reflecting what's happening in the population as a whole. So it relies on this idea of there being like a true distribution of exposure and outcome in the source population. For example, here, that's the number of people in the like town, like in the source population, that are exposure positive and disease positive, and there's a cell for each other combination of exposure and outcome. And this is more theoretical because you're not usually going and sampling an entire town. You usually take a subset because that's the whole purpose, is to get some efficiency from just getting a subset of the population. And basically, there is the same A, B, C, D distribution in lowercase, and like each one has a corresponding value in the source population, so little a in the sample population and big A in the source population. Sampling fraction is the value in the sample population divided by the value in the source population, and basically the value, like the sampling fraction for each of the A, B, C, and D cells, when they're equal or close to being equal, then that basically means that there is not selection bias. And whenever there is selection bias, it means that one of these values differs from the other three. So bringing this into an example, this is a cross-sectional study of smoking and lung cancer. We have 52 people that are smoking negative, lung cancer negative, 14 that are outlined in blue that are smoking positive, lung cancer negative, 8 that are yellow, smoking negative and lung cancer positive, 8 that are yellow and outlined in blue, so smoking and lung cancer. This is our source population, and what we want is to have a sampling fraction of 2, so we want a mini version of this population where each cell is scaled down by a factor of 2. So we know that the sampling fraction for this one is going to be it should be 1 over 2, and the sampling fraction is little a over big A. Big A is 8. So what should little a be in order to have it resolve to 1 over 2? Should be 4. We do the same for B. B has a denominator of 14, so we need 7 that are smoking positive, lung cancer negative, and we keep doing that for the other cells until we have this population that is basically a half scaled version of the source population. And that's an example where there's perfect agreement between the measure of effect of interest in both your sample and your source population, where it's A over B over C over D comes out to 3.7 in the source population, while in the study population it also comes out to 3.7. And that basically means that we sampled perfectly, but that's not always what happens. This is a situation where this smoking negative lung cancer positive cell was oversampled, and we know that because the sampling fraction in A, B, and D is 1 over 2. Well, it's 3 over 4 in C. It's higher than it should be. And the effect that has is to basically change our odds ratio, because before we scaled each 4 numbers in this equation down by the same factor, but now this value is scaled down by a different factor, so it changed our odds ratio pretty drastically, biasing it towards the null. And now just bringing this into control selection, just kind of switching gears. Now outcome positive is orange and exposure positive is outlined in green. What we do with case controls is the cases are usually pretty rare, so from whatever roster we're looking at, we usually take all of them. And what we do need to be careful about is how we select our controls. So we have this overwhelming amount of controls. That's kind of the way case controls work, is cases are rare, controls are a dime a dozen. So we want to sample these controls in a way that our sample that is chosen of controls represents the exposure distribution in this population. So bringing it back to our sampling fractions, that means that we're ignoring these disease positive and case ones, but we want the B sampling fraction and the D sampling fraction to be equal. So to do that, we would first figure out the capital B and capital D. So the number that are exposed, if we were to count them all up, is 20, and the number non-exposed is 40. And if we were to take a random sample of the group, we'd want it to be a consistent fraction of the larger population, really. So we know in the source population it's 40 and 20, found that here. And if we were to count up these ones, we'd see that there are 10 that are exposure positive and 20 that are exposure negative. And we can see that that's scaled this source population down by half. And yeah, that's just doing that math. The last thing I'm going to talk about is compensating bias, which is kind of neat. Just to make it easier to understand, I'm just going to show how you get the odds ratio into the cross product form. So like the classic way, it's a ratio of odds. The odds in the exposed, A over B, divided by the odds in the unexposed, C over D. But dividing fractions, you just reciprocate these, multiply across, and then you have AD over BC, the cross product format of the odds ratio. Basically, this compensating bias relies on the idea that if you change, let's just say, A and B by the same amount, you're changing the numerator and denominator by the same amount, and that would cross out. And yeah, that's what I'm going to show you in this example. So what that means is if as long as A and B, like the A sampling fraction and the B sampling fraction, are equal, they don't need to be equal to the C and D one, just as long as the C and D one are also equal to each other. So an example of that happening here is we have a sampling fraction here of 1 over 2, so 5 divided by 10, 1 over 2, 10 divided by 20, 1 over 2. And here we have 3 divided by 30, so 1 over 10, and 8 divided by 80, also 1 over 10. And they're not all equal, but the exposure positive row is equal to each other. They both have a sampling fraction of 1 over 2, and the exposure negative row also has equal, it's 1 over 10. And let's see what the two odds ratios are. 1.3 for the source population and 1.3 for the sample population. So basically what that showed us is as long as all 4 cells don't have to have equal sampling fractions, but as long as the two the exposure positive, this row has the same sampling fraction, it can be different from these two as long as they have the same sampling fraction. And similarly, disease positive and disease negative can have a different sampling fraction as long as these two cells are equal and these two cells are equal, because that creates another situation where something in both the numerator and denominator is being changed by the same amount. So yeah, I hope that was helpful.